Hi, everyone. Welcome to this afternoon's CERIAS security seminar. I would appreciate all being here. So today we're really pleased to have Mu Chang speaking virtually. So Mu is an assistant professor at the Kahler School of Computing at the University of Utah. So he works at the unique intersection between system security and cyber physical systems, which is very related to my current research. So I follow his research very closely. Okay, so Mu is the lead of a couple of projects. For instance, the DARPA project, Semantics-Aware Discovery of Advanced Persistent Threats in Cyber Physical Systems. So this project aims to detect advanced attacks in CPS settings. He's also a key personnel on the NSF CPS Frontier project, software-defined control for smart manufacturing systems. And he has led technical effort to develop a security vetting system for controller programs. So he publishes in top-tier security conferences, including IEEE Security and Privacy, CCS, and NDSS. And then he received a couple of awards, Distinguished Paper Award from ISTA, and also another Distinguished Paper Award from UPSLA. And also, I guess, back in 2020, you got the best paper honorable mention at CCS, as far as I remember, right? So welcome, Mu. Thank you so much again for being with us today. Please take it away.
Yeah, thank you, Berkey, for the introduction. It's my great pleasure to introduce our work as it's a prestigious seminar. So first of all, can you see my screen?
Yes. Yes.
Okay, great. All right, so today I'm going to talk about our ongoing project on backtracking intrusions in modern industrial Internet of Things, or IIoT. So the motivation of this project is very straightforward, right? So the threats are real, right? So you can see a lot of these news headlines about those different attacks, right, against the critical infrastructures. Right, so the adversaries have demonstrated their ability to attack different critical infrastructures, for example, water system, right, power systems, nuclear facilities like the Stuxnet attack, right, or manufacturing sectors like the Colonial Pipeline attacks. Right, so all these real attacks and their significant impacts, right, motivate us to develop new techniques that can help the human inspectors, right, to understand, to capture these attacks, right, new attacks against these IIoT systems. To understand the attacks, well, first we need to understand the system itself. Right, so now that we are at Purdue, right, it's necessary to mention this Purdue model, right, for the modern industrial control systems. And essentially, the entire control systems can be divided into multiple levels, right? Particularly 5 levels, right? From level 0 to level 4. And the lower the level is, the closer it gets to the physical domain. And for example, the level 4 is about the business logic, right? You can see a lot of business servers at this level, right? So the employees, admins can also connect their devices, right, to the internal network, right, through this level. So level 3 is about the engineering, right? So the operations, right? You can see these engineering servers, right? You can see some development workstations or data servers. But basically, this level 3 and the level 4 are still the traditional IT systems, and therefore they are kind of separated from a more physical domain, right? Through, for example, using a firewall. And the level 2 is actually more about the control systems, right? So you can actually see SCADA servers, right? SCADA is a short for supervisory control and data acquisition, which can be used to monitor the entire factory floor. You can also see HMI, human-machine interface, at this level, which allow the human operators to easily send command to the physical devices and get feedback. So the level 1 is called the intelligence system level, which essentially includes all this field controllers like PLCs, right? Process logic controllers or robotic controllers or some real-time controllers, RTAC. And all these different controllers are used to control different physical processes at level 0. And because this Purdue model is designed in a very general way, it can be used to support different physical processes. Right, so for example, these physical processes can be a water treatment system. Right, so therefore, these PLCs can be used to control the pumps that are attached to those water tanks or the chemical storage tanks, right, or mixers. Right, so this physical process can also be a power grid, right? So therefore, the controller is used to control the power generation, transmission, and distribution at individual substations. Or this physical process can be a manufacturing sector, and therefore, well, we're actually controlling robots, controlling the conveyor belts to deliver cargoes, and eventually send them to, for example, the highway warehouses. Because the industrial control systems must follow this Purdue model, so the attacks also follow this model. Right? Take this Florida water treatment plant attack as an example. So of course, right? So this attack itself is an insider attack, right? But now here I add some additional attack features, right, to make it more general. So essentially, the goal for this attack is to be able to compromise the water quality. But in order to do that, so what the attackers does is they need to first penetrate this system to get into the inside network, internal network. And to be able to do that, they can initially penetrate some laptop used by administrators, right, by using spear phishing. So then they can get into this internal network. But just to get into this internal network, it's not enough, right? Because the modern control systems can be very complex. It's not very easy for the attackers to identify the target that where they want to cause damage. So therefore, they need to perform some internal reconnaissance, right? For example, to penetrate this data server to get some sensitive information to understand where the high-profile targets are, right? So in this case, where this critical SCADA server is. And then once they have figured out this high-profile target, they can move laterally from one host to another, eventually get to this critical target. And starting from there, they can send fake commands or the fake configuration settings, right, to the field devices or field controllers. Right, so in this case, you can change the dosage of the certain chemicals. And upon receiving this fake commands or fake the modification of the configuration settings, right? So this field controller will eventually send a false command to the specific, for example, pump that is used to control the dosage of a certain chemical and eventually cause a water contamination. And in addition to that, the attackers can further hide this attack by providing fake measurement readings, right, from this SCADA server. So from this attack, right, from this typical attack, right, so we get two major takeaways. First of all, unlike the traditional attacks that target computer systems or IT systems, the attacks against a control system, modern control systems, aim to cause physical damage, right? Essentially cause the damage to level 0, right? So this physical processes. So in traditional attacks against computer systems, attackers usually focus on data, right? So they either steal data or they compromise data. In the attacks against control systems, although the attackers still need to perform cyber attacks, right? But the goal, the ultimate goal for this cyber attacks is to eventually cause physical damage, cause disruption to the production systems. All right, so this is the first key takeaway. The second key takeaway is that although the ultimate goal is to cause physical damage, right? So the intermediate attacks in the cyber domain are still necessary, right? So why is that, right? Because the attackers, in order to cause physical damage, they need to get into this internet network in the first place and be able to penetrate some internal hosts. they need to gather enough information about the system, for example, the topology of the network, right, or where the high-profile targets are. And eventually, as a remote attacker, right, so they actually need to send digital commands, right, from some digital devices to the field devices. So based on these insights, right, so we define the goals for our project, right? So essentially, we want to achieve two goals, right? So first, right, so we want to be able to capture, right? We want to develop a technique that can help the human inspectors, right, to capture how physical processes are compromised by malicious attacks, by malicious logic. The second goal is that we want to help them to discover how physical attacks are caused initially by cyber intrusions. To achieve these two goals, right, essentially we need to connect multiple individual attack pieces based on their causal relations, their dependencies, or in other words, connect the dots, right? So that means essentially we need to enable this provenance analysis, right? So in this new domain of industrial IoT systems. So provenance analysis is actually a well-studied topic in traditional IT systems, right? So in traditional IT systems, attacks are modeled using OS-level objects, right, such as processes, files, sockets, and their relations. So for example, if you observe a suspicious process, right, say a running process for the SQL Server, so then you can use this process-to-process relation to identify the parent processes that create this process. You can further use the file-to-process relation to identify the binary executable from where this malicious process is being created. Similarly, you can also use the file read, file write relations to identify what data has been leaked or what file has been compromised, so on and so forth. And eventually, you can trace back to the origin of this attack. In this case, is this malicious phishing email, which contains a malicious attachment. Although this approach is proven effective in detecting attacks against computer systems, we find that it may not be easy to directly apply this technique, right, to the new domain of industrial control systems. So this is because this OS-based provenance model can only describe the attack at a coarse-grained level. Right, so for example, in this case, well, it tells us that this SQL Server.exe is being leveraged by this malicious program, malicious process, right, to cause some damage. It does not inform us how this internal logic of this SQL Server has been compromised. So essentially, it does not capture the application semantics. So in fact, some prior work, right, actually from Purdue, right, from Professor Zhang and Professor Xu's group, actually shares the same insight. And they propose to instrument these application level programs, and so as to extract more semantics. So we argue that this semantics is actually of more importance when we capture attacks in the physical domain. This is because the physical processes, right, which is at the level 0, are essentially application logic, right, that is running on the lower level of control systems. To capture this application logic, to capture this physical semantics, a prior work, right, ProfThings, right, so also takes the same approach, right? So they basically instrument the application program so that they can monitor the critical functions at runtime. In addition, they also introduced a more comprehensive model, right, provenance model called W3C, right, ProfDM, right? So in this model, it basically associates some critical physical devices with some internal function calls, and they will also model the call relation, right, between functions. It also treats this system events, right, so application level events as some critical resources, and you will check, right, so what are the functions that create certain events and who are using those events. And by using all these relations, right, so eventually it can trace back to the origin of a certain activity. And in this case, it can indicate that this kitchen light is turned on based on the motion, previous motion being detected. So this is actually a good example of applying this provenance analysis to this new domain of modern IIoT. So essentially, we can take the same approach. However, we find that several major limitations of the prior work must be addressed, right, before we can apply this promising technique, right, to this new domain of industrial control systems. To understand the limitation of the prior work, right, so we use a motivating example. So from our test bed, right, so essentially we have this Fisher Technique test bed, right? So some context, right? So Fisher Technique is a German company which is focusing on this education for manufacturing. So essentially they build this miniature test bed. But because their goal is for education, right? So educating future workforce, right? So their test beds are designed to be precisely reflecting what is going on the factory floor. So for example, in this manufacturing test bed, right, so we have a high-bay warehouse, which is commonly used for a manufacturing floor to store the work pieces. Right, so we also have a vacuum gripper, which simulates the pick and place robots on the field. And we also have a multi-processing station and a sorting line. Right, so the construction of this entire test bed is highly flexible, right? So each controller has its individual controller program, and the entire test bed can be controlled either using a PLC or a computer program. And due to this high flexibility and high fidelity, right? So this test bed has recently been extensively used in research and education. All right, so for example, if I just simply search for these two keywords, right, Fisher Technique and security, I can actually find quite a few relevant papers. So we can actually perform a lot of different actions on this test bed. But here we just focused on two processes, right? So one retrieval process and one storage process for the high-bay warehouse. So essentially, you can actually store a workpiece, right, into an empty slot in this high-bay warehouse, and later retrieve it from this high-bay warehouse, right, for later processing. So the retrieve process is actually triggered by a human operator, right, by sending a request to the SCADA server. The SCADA server will forward this request to the controller of this high-bay warehouse. So upon receiving this request, the controller of the high-bay warehouse will first check the storage state, right, to locate, right, to identify where this the requested workpiece is. So this storage state is persistently stored in a file. Right? So this is because even if the system is restarted, the state will not get lost. So once the controller has identified this, has located this workpiece, it will request the gripper, right, to fetch this workpiece, and eventually it will update this storage state. The storage process, on the other hand, is triggered by automatically by a sensor event. Right? Essentially, when a new workpiece, right, has arrived, right, it's placed on this receiving station, right? So it will trigger this sensor event, which will further trigger this high-bay warehouse, right, to store this piece into this storage space. And similarly, it will also check the storage state, right, store the workpiece and update the state. So this is the normal case. So what can go wrong is that, so now that this storage state is stored in a file that can be exposed to the attackers. So what the attacker can do is, so they can change, right, directly write this file, changing the state, right, messing up the state, right, between two iterations, right, between this retrieval and storage, these two iterations. Right, to illustrate what happens, right? So we use this example, right? Suppose right? So this is the original state of the Happy Warehouse, right? So this Happy Warehouse has 3 rows, 3 columns. And initially, it holds 3 work pieces, right? 2 red ones and 1 blue ones. So then upon receiving the first retrieval request, right? So the gripper will grab this blue piece, right, based on this request, and then the Happy Warehouse will update the state, storage state. So then normally, if there is a storage process, right, storage iteration afterwards, requesting to store a blue piece into the storage, right? So this blue piece will be put into this empty slot at 0, 2, and this storage state will get updated. However, in the presence of an attack, right? So between these 2 iterations, the attacker can actually modify this state, right? For example, it can set this the 0, 1, this slot to be empty. So then the storage process afterwards will get confused and eventually cause a collision. So to capture this attack, right? So what we want to observe, right, from a provenance graph is like this, right? So first of all, right, definitely we want to observe this storage process, right? Because that's one that directly causes collision. And specifically, we start from this collision point. We want to be able to observe, right, what function actually directly causes collision, and what are the functions that can trigger this function. Further trace back, right? So we can identify the initial starting point of all these functions, right? Which is this sensory event, which is triggered by this newly arrived work piece. So in addition to that, we also see that this storage process actually need to read from a file, right, before it performs some action. Right, by using this data dependency, we can further trace back to see that, okay, so this file is actually updated by this retrieval process. Similarly, we trace back to find the initial point of this retrieval process, right, which is actually a legitimate command sent from the server, SCADA server. So in addition to the actions performed in the physical domain, we also want to see that who else has been writing to this file. So therefore, we further need to dig into this the digital domain and to see eventually see this file has been actually manipulated by a unknown process, right, which is actually created from file that is downloaded from a suspicious IP. So this is the expected result. Unfortunately, the prior work, right, prop things cannot help us to generate this complete graph. So the first limitation of prop things is actually related to our first goal. So our first goal dictates that the provenance analysis results, right, so must help the investigators, right, to understand how the physical processes has been compromised. So that means at least it needs to be meaningful to human readers. So that means, for example, by looking at this graph, right, we need to be able to tell, okay, so this is actually a retrieval process, right, which aims to fetch some items from the Happy Warehouse. So then the question is, how do we identify those functions that bear clear semantic meanings? To solve this problem, prop things actually rely on the source code level symbols. Right, so function names, which are not always available, and even if they are available, they cannot be trustworthy, right? Sometimes can be very misleading, right? Not precise. Right? For example, we have seen that some function are called is called fetch, right? But in fact, it's not used to fetch a item, fetch a work piece, right? So instead, it's used to fetch the container of a work piece. So then one may say, so now that you may not be able to precisely identify those functions, only the functions that bear a clear semantic meaning, so why don't you just log all the functions? Unfortunately, this does not work, right? Because when you perform those critical actions, the controllers actually also makes a call to a lot of additional functions. Right? If you log all the functions, the result will become very noisy. So this is the first limitation of the prop things. So essentially, it does not have a robust way to extract semantics from the controller code. The second limitation is also related to this G1, our first goal. Right? So essentially, the provenance analysis results, right? So must help the investigators to understand the text. So that means they must capture abnormal activities. So then the question is, how do you define what can capture abnormal activities? So let's take a look again at this example. If you just look at these two individual iterations, right? So this retrieval iteration and this storage iteration, both of them are fine, right? So both of them are caused by legitimate sources, right? So one is caused by a legitimate command from a human operator. The other is caused by a newly arrived workpiece. The attack actually happens in between, right? So which messed up the state transitions, right? Transition from one iteration to another. However, right, so this prior work, prior things, does not consider the dependency, the transition from one iteration to another, right? So instead, it only considers individual iterations to be independent. So what does that mean? Right, again, using its own example, right? Suppose we have two iterations of this same action, right? Basically, the light is turned on, right? So based on a motion being detected. Well, the first iteration looks fine, right? Because the light was off and now it's turned on because there's a motion. The second one seems more suspicious, right? Because based on this context, the light has already been turned on, but you actually trigger all the same functions that are used to turn on the light again. However, the prior work, right, prop things, may not be easily capture this inconsistency, right? Because it does not look at the dependencies across iterations. The third limitation of the prop things is related to our second goal, well, which is to capture the root causes of the attacks, the cyber attacks in the digital domain, which unfortunately cannot be achieved by prop things because it only looks at the physical operations, right? So for example, in this case, right, so at best, you will just stop here and will not further trace back to these the OS level, right, processes that actually caused by those malicious attackers, right, which tamper with this shared state. To address the limitations from this prior work, while enabling this provenance analysis in this new domain of industrial control systems, we proposed our approach, right? So ICS tracker. So essentially, ICS tracker takes the 3 steps. Right, so the first step is to recover the physical semantics of low-level function calls. So once we can identify only those critical functions that bear clear semantic meaning, right? So then we can selectively instrument and monitor only those functions at the runtime. So once we have identified those critical functions, we'll further perform static analysis on the controller source code, right, to identify the data dependencies among those critical functions, which can be invoked in multiple iterations of the same controller program. And eventually, once we have built the provenance graph for the physical operations, we'll further connect the physical logs to the low-level, right, OS level, right, system logs. Right, but this connection is performed in a selective manner, right, because we only look at those low-level activities that cannot be captured by these application logs. So now let's take a look at some details. All right, so our first step, right, so semantic recovery. Right, so the high-level idea is very straightforward. Right, so we don't want to rely on symbols. Right, so therefore, instead, we take a more robust data-driven approach. right? So essentially, we first instrument every single function in a controller program in an offline manner, so that when we run this controller, we can collect a function trace. So then we run a controller, right, to perform specific actions, right? For example, a retrieval process or a storage process, so that we can correlate this high-level physical semantics, right, with a low-level function call sequence. So the high-level idea is straightforward. However, it turns out to be a non-trivial task, right? So the major challenge, right, still comes from this huge noise. Right? So when you perform this specific action, right? So the controller code actually makes a lot of calls to a lot of not irrelevant functions. To precisely identify those functions, the critical functions, right? We need to remove those noise. To remove the noise, we need to first understand what are these noises. To our study, the noises come from three sources. Right, so the first source, right, the first category. Right, so in this category, the functions are always called, right, regardless of what physical actions are being performed. So that means you can always see these functions regardless of whether you are running this retrieval process or storage process or hybrid warehouse operations or this sorting line operations. And because they are always there, so that means that definitely they are not relevant, they are not specific to any physical actions. And therefore, we can identify this common pattern and remove them. So for the second category, right, so this noise actually comes from the execution variance. Right, so execution variance of the same physical action. Right, so even if you run the same physical action over and over again, right, because of the different inputs, right, different settings or different conditions, the program may take different execution paths, and therefore it will result in calling different functions or calling the same function for different times. So therefore, we want to eventually identify only the invariants, right? So those functions that are always called when we perform certain actions. So the third category. So in fact, the functions in the third categories are not necessarily noise. Right? So they are still inherent functions that must be called and always called when you perform a specific action. And the only problem is that they are just too low level. Right? So for example, if you want to fetch a workpiece from the hybrid warehouse, you actually need to call a lot of low-level movement functions. For example, you need to trigger the gripper to move up and down, right? So left, right, forward, backward, right? Move closer to the hybrid warehouse or away from the hybrid warehouse, right? So these low-level movements and the order of the movements, they are inherent features of a certain physical action. But the only problem is that if you log all these actions, it will be too tedious, right? So they are highly repetitive. And also, the semantics of these low-level functions, they are already captured, already covered by the high-level counterparts, right? For example, all these movements for this fetch is already captured by the fetch function. So therefore, we can safely remove these low-level details. So based on these insights, right, we designed our solution, right? So which takes us 3 steps, and each is used to remove one type of the noises. All right. So for example, the first step is to extract the common patterns between different operations, and this common pattern actually represents the noise, right? So in the first category, right? So for example, some low-level activities are used for network communication. Right, so regardless of what activities you are performing, right? So the machines, right, the controllers always need to report its state, right, to other machines, and therefore you always use the basic network communication functions. So once we have removed the first class noises, right? So then we further try to extract the invariance across the execution instances, multiple execution instances of the same physical action. Right. So the common pattern extracted from here actually represents the unique functions that will be called when you perform a specific action. But of course, those are low-level details are also included in this pattern. And therefore, we need to perform the third step, which use the frequency, the occurrence of the functions as indicator, right, to remove those highly repetitive low-level details. So for the second step, right, so we want to identify the cross-iteration dependencies. And to this end, we perform static program analysis on the source code of the controllers. And specifically, we first identify all the file read-write. And then starting from there, we perform backward data flow analysis to identify their sources. And if it turns out that multiple read-write share the same data resources, and then we'll further perform control flow analysis to identify the critical functions that actually share this shared state. So once we have identified the shared state from static analysis, we'll further aim to recover the state transition at runtime, right, by using the application log. Right, so in this case, so when this state is being loaded for the first time, we will also initialize the internal state, right? So, so then when this state is being updated by a write operation, we'll also update this internal state. So next time when the controller loads this state again, right, from the shared state file, so we can actually compare our internal state with the loaded state to see whether there's any inconsistency. So essentially, we can reconstruct this state at every single point through this process, and therefore provide additional information to the human investigators, right, to help them to make decisions. So the third step is a selective causality tracking, right? So in the digital domain. So the rationale behind this selective approach is that for all these application logs that access the shared state, right? So shared file, for example, you can actually also see the corresponding logs from a lower level, right? So now that we have already captured more detailed, right, semantically clear logs from the application, we don't actually need to collect those logs at the lower level. So instead, we only need to focus on the delta. So as I mentioned, this is an ongoing project. So we're working on the evaluation, and we have already created different attack scenarios for that purpose. And some preliminary results are promising. It shows that our data reduction is significant and accurate. For example, for the motivating example, while the original log size is 20K, but after several levels of reduction, we can reduce it to 33, right? 33 entries, which can still capture all the critical functions in the retrieval process. So in the meantime, we are actually developing new test beds, right, so as to validate our approach on different environments. Okay, so in conclusion, right, to capture attacks in this modern industrial IoT systems, we propose a cross-domain, cross-iteration, semantics-aware provenance model. And particularly, our semantic recovery is reliable and automatic, right, because it's based on data mining, right? So mining the correlation between physical actions and the function calls. So our provenance analysis also considers the contextual information of our physical processes, which could be strong indicators of attacks. With that, I conclude my talks, and I'm happy to take questions. I've already seen some questions from the Q&A. Let me just read it out loud. So what is the margin of error that can occur while determining whether a function is critical or not and what steps have been proposed to monitor those probabilities? That's a great question. So currently we are taking a empirical approach, right? So based on evaluation, and I believe this actually related to a lot of threshold, right, parameters, tunable parameters used in our mining, and to give a good answer, we definitely need to perform more experiments, right, to test what parameters can actually give us better results.
Okay, I think this is the only question that I see on the Q&A. So
yeah, I see another open one. How you determine when to stop collecting logs? That's also a good question, right? So essentially, we don't know the precise timing, right, to stop the logs, right, to stop the collecting the logs, right? So when we do the data mining, but that's why we do the data mining, right? So essentially, based on our data mining, we expect to identify only the common parts, right? Only the invariant part, while we can remove those noise. And this noise actually is introduced, for example, like you said, right? So one source, right, to introduce this the noise is actually because we don't know when to stop collecting the logs and introduce additional logs which are not relevant to the specific actions we are looking at.
I think we have another question.
So given the rapid evolution of both cyber threats and industrial IoT technologies, how adaptable is ICS tracker to emerging types of attacks and advancements in IoT technology? Additionally, what are the key considerations or challenges when deploying ICS tracker in real-world industrial environments beyond testbed scenarios? So first question, how adaptable, right? So essentially we are testing this. So that's what we are actually considering how to adapt this system to different test beds or different environments. That's why we want to validate the same approach, right? So in different test beds. So conceptually, this is adaptable, right? So we can instrument the code at different level, right? So we can instrument, for example, more general, right? C code. We can instrument the structured text, right? So we can instrument some dedicated controller code. But yes, right, so I believe that this is also related to the second question, right? Deploying this technique, right, to the real systems can be challenging, right? So there are a lot of constraints, right? First, for example, first of all, based on my experience, right? So the domain engineers may not be happy if you want to touch their system, right? So they want their system to be as stable as possible. And instrumentation, you know, is by nature, it's a kind of an invasive technique. So whether they allow us to instrument their code is still questionable. And also, another consideration is the performance, right? So that's why we perform a selective instrumentation, right? So that's right. So that's actually also a concern from the prior work, right? Prof things, right? So in their paper, they also mentioned that if you instrument every single function, that will cause a lot of runtime overhead. So that's why they use a different approach to selectively instrument the function. And so basically what they do is they can use some data dependencies, right, to figure out what are the relevant functions, right? So by relevant, what they mean is they first identify some important data sources, important events they want to look at. And then they will just look at the functions that are actually accessed, that actually use those events. So we are taking a different approach, right? So we are actually trying to identify those high-level functions that are specifically used in certain actions, while ignoring those low-level details.
Okay, I think we don't have any other questions. So I have a couple of comments because I do work in similar domain. We have a couple of ongoing projects, especially in cyber physical systems. So whenever we use the data collected from a plant or autonomous vehicle or any other system, there are two things that we always get, right? So one of them is the completeness of this data. So I think one of the question was in that way, like how do you know that data represents the entire behavior of the system? What if I change a small configuration parameter, such as in your case, let's say there is the robot has a speed, right? You change the speed. And then like, how do you capture that? Right, this is the first question. And the second one is basically like, how do you ensure the data that you are collected is all benign traces? How do you know there is no faults or any other irregularities doesn't exist in the collected data? So what do you think about these two aspects when you are doing this research?
So basically, you are asking about the data quality and the data completeness. So to be honest, I don't have a good answer or a very good answer for that. So we're actually facing this question. So when we were submitting our VPRC paper, right? Because in that work, we also need to collect the data, right? So in test run and use that as a way to establish the baseline for the system, right? So I think that's a more general challenge, right? So essentially, it's the fuzzing problem, right? So this is also a challenge for dynamic analysis for fuzzing, right? How do you improve the code coverage? How do you make sure that you can access all the paths in the program, right? So we are actually taking just a best effort, right? So we run this program with different inputs, right? So in a kind of black box testing manner, and collect the different traces. So this is the best we can do. For the quality, that's a good question. So essentially, so previously we just assumed that the system is running normally. But in the case that it actually caused a fault, and unfortunately, that fault is also captured by the logs, right, for the training. So I would say, similarly, we can collect a lot of logs, a lot of traces, right? So assumption is that this fault is not a very obvious. We cannot be triggered very often, right? So of course, if it can be triggered very often, it's actually part of the baseline as well, right? So if not, then so that can be actually eliminated by using the mining approach.
Okay, makes sense. So I have a quick follow-up question. So based on the testbed, Fisher technique testbed, that what I understand is it's more deterministic, free from any like physical processes that we have seen in chemical plants, for instance. That's right. Right? So do you think that if you try to generalize your framework to other systems, there would be some challenges because of these complex physical processes or not?
I think so. So I think this testbed is not only deterministic, but also it's a discrete control system, right? So basically, all the actions are triggered by events, right? It's not like the continuous control system where, for example, this chemical process is actually purely triggered by how much chemical, how much dosage, right? So you actually fill in this tank, and so I believe. There is some difference, but at the same time, right? So in some previous work, So what I have observed is that for those continuous control system, what people usually do is they will try to discretize it, right? So for example, for this water level, right? So this water level in this water treatment plant, right? So instead of just monitoring this this water level as a continuous parameter, they will actually discretize it, right? To basically treat it as a high level, low level, medium level. And then, right, so basically we can apply the same techniques, right, which is already applied to this discrete system to this continuous system.
Okay, okay, makes sense. All right, I think we don't have any other questions. So Professor Mu, I would like to thank you again for joining us today. And I hope that in the future, you can visit Purdue in person and we had a chance to discuss more, and you can also talk to interested students here at Purdue.
Mm-hmm.
Thanks so
Thank
much.
you for having me. My great pleasure.